Dear students, today we will study about the electrical energy and power. We know that inside a conductor, the charges they do not flow in one particular direction at their own. Neither the electrons or the other charges to move them in one particular direction. That means for the flow of the current, potential difference is required to be applied across the ends of the conductor, as we are seeing that suppose this is a conductor and the electrons are free, some electrons are free in it, and their motion is random if we do not apply any potential difference across it. So they do not make any current. But in order to constitute a current through the conductor, we have to apply a source of EMF across the ends of the conductor. That means we have to apply a potential difference across the ends of the conductor, and this we can do with the help of the external source of EMF, say battery, cell, transformer, etc. Now, inside a conductor, the electrons they move from one direction, one end to the other against the direction of the electric field. And when we say current is flowing, say I current is flowing through it, the positive charge moves from higher potential to lower potential. Let this conductor has VA, the potential at this end, and VB, the potential at this end. Clearly, as the current is moving from point A to point B, VA will be greater than VB, or we can say VA minus VB is greater than 0. That means it is positive. Now, the charges which are at end A will have higher potential energy, and when they reach to point B, they will have less potential energy. Suppose for charge Q, potential energy at point A let it be Q into VA. That means the potential at point A and the charge. And this charge let reaches to point B in time delta t. In time delta t, let Q charge reaches to point B. So potential energy of charge Q at B is Q V delta B. Now change in potential energy of charges Q will be equal to the potential energy, final potential energy, that means at point B, minus initial potential energy, that means at point A. And we can write it as delta U potential is equal to Q into V delta B minus Q into VA. Or we can write as Q is equal to I delta T. So this will be equal to I delta T VB minus I delta T VA. Clearly, I delta T into BV minus VA, this is less than 0, means this is negative, because BV is less than VA. The charge is moving from higher potential to lower potential. Or we can write delta U potential is equal to minus I delta T into the potential difference. We have taken V is equal to VA minus VB the potential difference. Now this is the potential energy. The change in the potential energy of the charge is delta Q. Now, if this charge is moving without any collision, if no collisions of charges delta Q during its flow, then this change in potential energy converts into the kinetic energy of the charges. That is delta K is equal to I delta T into V. And as the kinetic energy increases, we consider and we know that the charges will be accelerated. So, charges can be supposed to be accelerated. But as we have seen that charges move with an average drift velocity. So, where this kinetic energy of the charges go, where it is dissipated. So, for this, we say that during collisions of charges with atoms during their flow, the kinetic energy of charges. Kinetic energy of charges means the kinetic energy which is increased due to the decrease in the potential energy is transferred to atoms, which in turn vibrate more vigorously than, and hence heats up. Thus, the energy dissipates in the form of heat in the conductor. The power loss or energy loss is due to this heat. Power, as power is defined as energy dissipated per unit time. So, power P is equal to delta K by delta T, that is equal to I delta T into V by delta T, or we can write IV or VI as the power dissipated. If R is the resistance of the conductor, then P is equal to I square R. Also, P is equal to V square by R, as V is equal to IR. This implies I is equal to V by R. So we have seen that power is equal to I square R. So power is directly proportional to R, and power is directly proportional to I square. For long distance transmission of electrical energy, we cannot neglect or reduce the resistance of the transmission cables. Therefore, the electrical energy or electrical power is transmitted at high voltage to reduce power loss. If P is the power to be delivered to a device at voltage V and current I, then this will be equal to P is equal to I square R, and P is equal to V square by R. For long distance transmission, the voltage applied, if it is very high using the transformers, then the power loss is reduced considerably.